we are fortunate to have Professor Shuran Song from the Computer Science Department at Columbia University. And Shuran did her PhD at Princeton and her bachelor degree from HKUST. And during her PhD, she also spent time working at Microsoft Research and Google. And Shuran's works span across 3D vision and robotic manipulation. She was part of the MIT Princeton team for the Amazon Robotics Challenge, winning the 3rd place and the 1st place in 2016 and 2017. Her papers have won a number of Best Paper Awards or Best Paper Award finalists in CVPR, ISS, ECORA, and IROS. With all that, I'll hand it to Shuran.
Okay, cool. Can you guys hear me?
Yep. Your slide still looks just a little blurry, but maybe it will get better in a few seconds.
Hopefully it will be okay.
Yeah, it's getting better on my end.
Okay, nice. Yeah, and there's if you have trouble looking at any of these videos, I think most of those videos is actually also online in our webpage. Yeah, so okay, so hello everyone. Very nice to be here. So today I'm going to talk about visual learning and reasoning for deformable object manipulation. Okay, so let's start. So we know that deformable object or deformable class is like really everywhere in our daily life. So here is just a very simple example. Every morning, the first few things that you might be doing is probably like making your bed, wipe your face with a towel, put on your shirt, and deciding whether you want to wear a mask or not, right? So during this process, you can effortlessly manipulate all this deformable class even before you really fully waking up. However, this kind of like similarly trivial task of accurately manipulating deformable objects is still a pretty open challenge for today's robotic system, which are often designed to handle very rigid objects with very rigid movement. And I think a natural question that we really need to ask first is what are the things that make deformable objects so different and therefore difficult for a robot system to perceive and manipulate? So here are just a few main reasons, like in my opinion, that make them difficult. So first is that for deformable objects or class, they're often highly under-actuated. So what that means is that when a robot is manipulating or holding a piece of cloth, all it can control is a very small region of the cloth around its gripper. And the system do not really have much control or direct control over those out of contact positions. Right. Another challenge is that the system also needs to deal with extremely high degree of freedoms when they're dealing with deformable objects, especially in comparison to rigid objects, whose pose can be typically fully specified with a few numbers. And the third is more specific about their geometries. So for objects like cloths or garments, they often consist of very thin 3D geometries that are not watertight. So these kind of unique geometric properties make them ill-suited for typical 3D shape representations that are designed for solid objects, such as occupancy grade or sun distance functions. So this kind of require us to really think about the potential new shape representations. So, and finally, because deformable cloths, they are so thin and they can deform in so many different ways, they often experience the most extreme case of self-occlusion, especially when they are folded or crumpled together, which make the perception and planning task extremely difficult to handle those kind of objects. So due to all these challenges, prior works on garment or cloth manipulation often build on top of some simplifying assumptions, such as assuming high visibilities of the cloth or rely on like very strong prior knowledge about objects, such as a very accurate 3D mesh of the object instances. So the goal for today's talk is we kind of want to relax some of those assumptions just a little bit and try to answer the questions of how we can effectively enable the robot system to perceive and interact with a piece of cloth under severe self-occlusions. So that's why we have this title, Unfolding the Unseen. And concretely, I will talk about two projects, and one is more focused on perception, the other more focused on manipulation. Okay, so let's start with the first project. So the goal for this project is actually try to perform category level pose estimation for garments like t-shirts or tops, this kind of clothes. So in this project, the first question, and also I would say probably the most important question we need to answer is how should we define the pose given a piece of garment, right? So if we look at rigid objects, the definition is very clear. Given any object instances, its pose or configuration can be fully described by 6 degrees of freedom, including 3 degrees of freedom translation and 3 degrees of freedom of rotation. To extend this definition to a collection of object instances, we just need to define a shared category level canonical pose. So for example, for camera category, we can just use the direction of the camera lens to align different object instances and use that orientation to define a shared canonical pose for this category camera. And then the task of category level pose estimation is then defined by inferring the corresponding transformation between the observed object instances to this canonical pose, whereas observed object instances can be something that the algorithm have never seen before. So we call this representation a NOX, which stands for normalized object coordinate space. And a similar idea can also be extended for articulate objects, just with a few additional degrees of freedom describing the object's drawing parameters. Okay, so but how about for deformable objects, right? How can define a pose for a t-shirt? Are we going to specify the positions of every single vertex on the shirt? Well, actually, the short answer is actually yes. And since a garment has such a high degree of freedom, in order to fully specify its configuration or pose, we kind of need to specify every point location on the t-shirt surface. And even more, we also need to specify the position for both observed and unobserved surfaces. Since we no longer have the rigid body constraints, therefore we cannot directly solve the pose for the unobserved point using algorithms like RANSAC, right? So obviously it is a lot of information to infer, and in some sense it's like too much for the network to infer. However, since all this kind of all those degree of freedoms, they are not completely independent. Therefore, there are some very strong prior knowledge or constraints the algorithm could leverage to simplify the problem. So the key question now is how we could impose those constraints or prior knowledge. Again, we can define a category level canonical space across different garment instances. So here, the canonical configuration of a category is defined by the garment geometry worn by a person in a T-pose. So one way to understand this canonical space is that given a coordinates in this canonical space, it will map to a similar surface location on different garment instances, which means that they are very likely to share very similar local geometries or semantic meanings. So for example, here, all the 3D points on the shoulder should have similar canonical coordinate labels. So with this category level pose estimation, we can now finally define the task. So given a partial observation of unseen garment instances, the goal of the algorithm is to map all the observed points into a category level canonical space. But how about for the unobserved surfaces? Well, remember, we no longer can use the rigid body constraints to solve those positions using RANSAC. So what we do is we will ask the algorithm to complete the garment's full 3D geometry in this canonical space, and therefore provide the pose estimation for those unobserved surfaces as well. And finally, we will need to map this completed shape back to the observation space so that the outputs can directly describe the garment configuration in the same observation space. So to summarize, the key idea for this project is really to formulate the task of deformable object pose estimation as a shape completion task in the canonical space. So first, by mapping the observed points into this canonical space, we estimate the pose for all observed points. And then by completing the shape in this canonical space, we estimate the pose for all the unobserved surface as well. And since the completion is happened in the canonical space, the algorithm can leverage a much stronger shape prior that are invariant to object configurations. So this is really the key idea of the project and also the approach. So in the next few slides, I will just cover a few most important design decisions for this algorithm. So first, how to get input observation. Right, so in this project, we actually less interested about the task of on-body class perception task, where the class is already worn by a person. So instead, we are interested in estimating the garment's pose or configuration under any arbitrary configurations. However, if we do not pose any constraints on the input configuration, the task can be quickly become too hard or impossible to solve. So instead, we will use very simple robot action to transform the class from arbitrary configuration to a configuration that is more trackable for the perception algorithm. So what we do is that we will ask the robot to randomly pick up the garment from any location it can. And by using this very, very simple pickup action, the system is able to reveal a lot more surface area on the garment by leveraging the gravity force. And also at the same time, the pickup action itself is very simple and does not rely on any prior knowledge of the class or its pose. Okay, so now we have the observation, input observation. After that, the algorithm will label all the visible points with their canonical coordinates. And we just use a standard planet architecture for this task. And also in this task, we can propagate the grasping point that's where the robot pick up the class into this canonical space using the predicted Knox label. And then the algorithm will need to complete this shape in this canonical space to provide labels for unobserved surfaces. So the task of shape completion for rigid objects is actually a very well-studied problem with many existing algorithms. However, for garments, because they're thin 3D structure, it's actually a bit tricky for selecting the right 3D shape representations. So for example, the typical occupancy grid is obviously not a good choice for representing thin surfaces since its accuracy is limited by the voxel resolution. But on the other hand, other representations like sign distance function like TSDF are able to represent thin structures by using the zero crossing surface. However, it can only describe watertight surface with no holes, which means that if we directly extract zero crossing surface, we'll get additional surface around the garment's openings, such as neck or waist. So to address this issue, we actually used a different shape representation called generalized vanning number field that allows us to represent thin surfaces with openings at the same time. So without getting into too much details about the vanning number field, here I'm just going to show you some of the shape completion results using different shape representations. So on the left, you can see that the canonical coordinate prediction on the top and also the ground truth surface that for this object instances, which is a top. And we can see that with on the right is basically the shape completion results using different shape representations. So we can see that with the vanning number field representation, the algorithm is able to represent very thin surface with the correct openings. While TSDF will not be able to represent openings, and occupancy grid will have trouble representing very thin structures. Okay, so now we basically has all the major pieces for the algorithm, and I'm just going to quickly show you some of the results from GarmentsNet algorithm. So here is example results for dress. On the top row is a prediction for each of the algorithm steps, that's the canonical coordinate prediction, shape completion, and also the mapping to the original input observation space. And the bottom row is a ground truth shapes. And here is another example for top. This is a jumpsuit. So so the data set we use is called Cloud 3D, and I think they provide around 6 object garment categories. And here are actually some results using real-world RGBD data. And if you're interested, you can definitely go to our project webpage. I think there are a lot more results and also details about the algorithms. that you can find in the project webpage. Okay, so to summarize, the key idea for GarmentsNet, the project that I just talked about, is really about the problem formulation, where we formulate the post-estimation problem for garments as a shape completion task in the canonical space. And by leveraging the category level prior about garments, the algorithm is able to infer the full configuration of an unseen garment using both, including both observed and unobserved surfaces. So this project is actually, as you can tell, mostly about perception, but the only step that actually involves the robot is step 0, where we ask the robot to pick up the clothes in order to observe it. However, this very simple action is actually very, very critical since it significantly reduces the difficulty of the perception task. So this got us thinking, what if the robot is able to use its own action to really physically unfold a t-shirt? Well, it just makes the perception algorithm so much easier, right? So in the next project, we'll push a little bit more on the interaction side and see how we can enable a robot to use this physical action to actually unfold a cloth and in order to reveal the unseen part of the cloth. So this is FlingBot that's I'm going to talk about. So, okay, so let's first talk about the task of cloth unfolding, where the objective is very simple. It's just to maximize the visible surface of a cloth. So this task is actually very useful and fundamental since that it's pretty much is a common first step for almost any cloth manipulation pipelines. Right, so by unfolding a cloth or a garment, we are able to reveal many key features on the cloth that are initially hidden in the original configuration, and therefore simplify the later planning and perception tasks. However, while the objective is very simple, learning a policy that can effectively unfold an arbitrary cloth is quite challenging. So here are videos of 2 robots that's actually trained to unfold a t-shirt using only pick and place actions. You can see that it will take a very long time and many steps to make just some small progress. And actually, if the corner of the cloth is unfortunately not visible in the initial state, the system will not be able to make much progress. And similarly, if the cloth is larger than the robot's reach range, the cloth will actually never be fully unfolded. So this system actually reflects a common limitation for many prior works in cloth unfolding, where the robot can use only quasi-static interactions like pick and place to perform this task. So over the past decades, there have been many works on this cloth unfolding task. And there also has been so many sophisticated algorithms and methods proposed to model deformable objects. However, the final systems are oftentimes highly inefficient, and they can easily take hundreds of steps just to unfold a very small piece of cloth. So here is actually an example of the robots that actually take more than 100 steps to unfold this very small piece of cloth. So as a result, many works in cloth manipulation considers a much simpler case where the cloth is almost unfolded and their key features are already visible in the initial state. So, but let's take a step back and really to think about what would you, what kind of action or what kind of interaction you will use to unfold a large piece of cloth like a blanket. So will you carefully pick and place every single corners of this cloth? Probably not, right? So instead, what you'll probably do is something very similar to this, where you will grasp the a blanket with 2 hands, stretch it, and fling it over the bed with some high velocity actions. So this example shows that what is really missing for our robots is the capability of using some high velocity dynamic manipulations in order to interact or manipulate deformable objects, which is something that we actually, as humans, constantly using in our daily life in order to improve our physical reachability and action efficiency. So fundamentally, what dynamic manipulation gives us is the ability to use high velocity actions in order to control those under-actuated objects without direct contact, and therefore efficiently expand the system's effective reach range. So using this idea, we designed our system FlingBot, which is a fully self-supervised system that is able to achieve over 80% coverage with, on average, 3 interaction steps. So in our experiments, we actually use 2 UR5 arms with 2 RGBD cameras. So the first one will take a front view of the workspace after the class is being picked up. And the second camera will take a top-down image used for predicting the grasp positions and also evaluate the unfolding progress. So what the algorithm do is to take those visual image as input and then output the parameters for the Fling primitive, which we'll talk in a bit. And after each action, the top-down camera will capture an image of the cloud and compute the delta coverage of this cloud that is before and after this interaction, and use that as a supervision signal to supervise the network training. And then in the end of each episode, the system will automatically reset the class initial states by randomly pick and drop this class back to the workspace like this. So the whole, as a result, the whole system is able to kind of learn how to unfold the class with only self-supervision signals from the top-down camera. Okay, so here is a very high level, I'm going to give you a very high level descriptions of our designing of the Fling primitives. So the system basically will need to first find 2 grasp points to pick up the clock, stretch the clock as basically as far as possible, and use high velocity swing action in order to fling the clock forward, and then finally place them down back into the workspace. So in order to perform this Fling primitive, the algorithm basically need to infer the parameters for each of these actions, such as where to pick up the clock, how far to stretch, how fast to fling, and also where to place the class after the fling action. So for the task of class unfolding, actually some of the steps, we have pretty trivial solutions. For example, for step 2, for unfolding, we probably just want the robot to stretch the class as far as possible. And for the step 4 is basically placing the class in somewhere reasonable will be okay. And therefore, the key part that the algorithm need to learn is where to pick up the class and how fast to fling. And so basically, the task for the network is to learn those parameters through this self-supervision signal. So due to the time constraint, I will probably skip the details of the network architecture, but you can check it out in our project webpage and also the paper. So instead, I will directly jump into the experiment and show you the system in action. So here is a simulation environment that we use for doing application study. So our policy is trained on a rectangular cloud with different sizes. And we also explicitly test the algorithm with larger rectangular class that is actually larger than the system's maximum reach range. And finally, we also test our system or policy, the learn policy on unseen t-shirts that the system has not seen before during the training. So as we'll see show later, even though our policy is only trained on rectangular cloth, it is able to perform reasonably well on shirts with different shapes. Okay, so here is the system in action. So you can see that we on the left, we show the pick and place baselines for the comparison, and on the right, you can see the FlingBot in action. And on the bottom, you can see the plots is basically showing you the class coverage with respect to the interaction steps. So in general, FlingBot is able to reach over 80% of coverage within 3 interaction steps, while the baseline system that's using only pick and place actions is typically stuck at around 60%. And here is a result of unfolding a t-shirt. Yeah, I think at this step, FlingBot is pretty much done, and the pick and place system is still trying to make progress. So here are more results of FlingBot in action. You can see this actually interacting with, like trying to unfold different shirt, different cloths with different sizes. And if you're interested in watching more of FlingBot videos, you can check out the project webpage. You can find a lot more videos there. So to summarize, the goal of FlingBot is basically trying to demonstrate the effectiveness of dynamic manipulation for the task of class unfolding through a self-supervised learning framework. So more specifically, by using dynamic manipulation, we are able to improve the system's efficiency, increase its effectiveness, effective reach range, and also achieve a good generalization for out-of-distribution cloths. So for example, we train on only rectangular cloth, but it's also work on t-shirts. Right. So to summarize my today's talk, I basically covers two of the projects on deformable cloth perception and manipulation, where we're trying to answer the question of how to enable a robot system to effectively perceive and interact with a piece of cloth under a severe self-occlusion. However, each of the project actually demonstrate a slightly different idea and approach. So for example, the first project basically is trying to leverage this a very strong category level part of garments in order to infer the unobserved surfaces, while the second project use robust physical interaction or action to really unfold the cloth in order to review the unobserved part of the cloth. And that's the end of my talk, and I'm happy to take questions.
Thank you, Shuran, for the great talk. We can have questions for Shuran. One question from Kaker for the post-estimation of garment. Is the label of the garment type given to the algorithm?
Yeah, so that's a good question. So it is, I think you can basically think that it is given because we actually train a different network for different categories. So I think that's something that the algorithm already aware of. So they know that it is a t-shirt, it is a pant. Therefore, it can leverage this category level part.
Thank you. There's another question from Aka. For the GarmentsNet paper, did you consider a pixel-wise contrastive loss to learn the category level correspondences? Or is it a learn the point-to-point mapping?
Yeah, so in our implementation, we actually take a very naive approach. It's basically fully supervised and it's pixel to pixel, is point-to-point mapping. So because we can get the training data in simulation, so we can actually provide point-wise label for each of the observed surfaces. So we directly use that as a supervision to train the network. But I think it's actually a very interesting idea to use contrastive loss or other like weaker supervisions to train this network. And I think that will be particularly useful if we want to train on real world data that is not as nice as simulation data that provides all the ground truth labels.
Another question is your wrap field parameter right from the metric, or is it point-to-point random map? If you can see the chat.
Oh.
Also, is your
okay. Field. So the wrap field, I think is probably the question is about the last step, which is mapping from the canonical shape completion results to the original observed space. So actually, in our paper, we implement two approach. So I didn't get the time to cover that, but the first approach is actually using the physics simulator. So we don't need to predict or learn anything because we already have the completed 3D mesh of the class, and we also know where the robot actually pick up the clock. So we can just run a physics simulation to perform this warping to the original observation space. So that's one approach. The other one is actually predicting this warp space. So what we implement is just directly point-to-point mapping without any constraints. So as you can imagine, this two method has very different advantage and disadvantage. The one with physics simulation, it's always generating physically possible results, which typically looks much better. But for the other approach that's directly learning the mapping, they actually typically give us more accurate prediction by directly regressing those coordinates. So we have both result and method in our paper for comparison.
Thank you. There's one question from Dave. What's insight from FlingBot sorry, it's another question jump up. What's insight from FlingBot can help you learn to achieve other dynamic interaction tasks, such as playing sports for robots?
Okay, so I don't know whether I can answer this question that well, but I think I think from what I learned is that actually by using those kind of high velocity actions or dynamic manipulation, we can actually make a lot of problem easier, especially when we're dealing with under-accurate systems. And I think playing spots is a great example. I think most of the spots actually involve high speed, like high velocity actions. And there's a lot of things that actually requires a lot of practice for human in order to do those actions very accurately. But a robot actually, once they learn it, once they get it once, they can actually repetitively perform that task very well. So I think like dynamic manipulation is really something that's underexplored, but very exciting.
Thank you. One more question from Edward. For one of the unfolding videos, I noticed the robots need to move back after each action, presumably to occlude the view for the perception network. Can this method work in situations with more partial occlusions?
Yes, I think the observation is correct. The reason why the arm moves back is so that the top-down camera can take a good pictures of the class after unfold or after each interactions, so that they can calculate the accurate delta coverage before and after interaction. So I think this is, I think it can be solved by, for example, adding more cameras or changing the camera location slightly so that the robot's occlusion is not a big issue. But I think the system is indeed able to kind of handle to a certain degree self-occlusions caused by the class itself. But the occlusions from the robot, I think we didn't really like try to handle that. That's why you see observing that kind of motion.
Thank you. I think that's all the questions. Thanks again, Shuran.